hand it to you, André.
Well, thanks a lot. So welcome everybody for being here, for your interest. Here is a bit of an overview of what I want to talk about. Yeah, we'll have to see how we do with time. We have about 40 minutes now. I may skip some things, but yeah, we'll see. So what I want to talk about, this long title can be split up in different parts. So talk a bit about trusts, what it is and how it relates to AI, about different aspects of hybrid AI, and then especially also talk about interaction in teams in trustworthy respects. And then there's a concept I call epistemic orchestration that I may elaborate a little bit on, maybe even talk about the use case where we use this. So let's just dive into it. So if we talk about the first aspect, so trustworthiness of AI, one short definition could be that we say that AI systems are trusted when we have confidence in the decisions that they take, so that we understand why those decisions are made. But of course, that doesn't, well, that's an understandable definition, but it doesn't help you as much in figuring out how to make systems trustworthy, because trust is not something that is just an aspect that can be added to a system and then it is trustworthy, but it emerges from various aspects that contribute to it. And I've mentioned here a few of those, so like fairness, robustness, transparency, verification, and accuracy, which are all important parts. One thing that I want to highlight here is, with respect to fairness, one part of that that I mentioned here is bias awareness, because very often bias is seen as something very negative and something that we need to get rid of. But in fact, I think that is a wrong perception, because bias is actually a means to represent information. So if we get rid of all bias, then we basically have no information left. So what is important here is that we are aware that there is bias and which bias there is in a system, rather than trying to get rid of it. So if you know, for example, on which type of data a system has been trained, then we know in which situation it can be used. And if we use it in the wrong context, then of course we get into trouble. That's what I would call bias awareness. And you will see a lot mentioned about the transparency in slides. But let's dive a bit deeper into the definition of trust itself. So trust has two main aspects. So and there are two words that are often used and confused. So one is trust, and the other one is trustworthiness. If we look at the relationship that we have, if typically a human user uses or operates an AI system, so we have the two roles of a truster and a trustee. And what we can say is that the trustworthiness is a property of the system, so of the trustee, which means that a system is trustworthy if it operates according to the specifications. So if it is correct, if it does what it is supposed to do. And the truster trusts the system based on the experience and of the understanding that it has about what the system is doing. And if we go further, we can say that there is, in the ideal case, you would specify a contract between truster and trustee so that the expectations and the specifications are made clear, in order to avoid what is called also as trust calibration. So trustedness and trustworthiness need to be calibrated in the sense that if they're not, then we get either the problem of under-reliance. So if we don't rely on a system, so it would be okay to use it, but we cannot use it, or we don't want to use it, which is a pity. But on the other hand, if we rely to it too much, then yeah, it doesn't perform as it should, and then we also get in trouble. And related to this, there is also, so if you have this understanding can be kind of different aspects. One called intrinsic trust. So if we really understand how a system operates and we agree with that, or extrinsic trust means that we trust the system from experience, or we trust that someone else actually understands it. But these are important concepts to take into account. And both these notions of intrinsic and extrinsic trust are also closely related to explainability, which also has different aspects. Now, of course, there is what you already mentioned also is that there is an AI act being prepared in the EU to exactly describe all these aspects of how trustworthiness in AI can come about. And they made a long list of aspects that they care about. But this is also, I just show this as an overview. It's very high level. So it doesn't help us in defining exactly how to make systems trustworthy and even to verify those. So there is still a lot to be achieved, but this is a good starting point. What is important to see is that there is in this framework, they have a certain definition of risks and riskiness of systems, and but there are different levels where the most important ones are the ones that are called high risk. So you have unacceptable things that you just do not want to have at all, like automated weapons and that kind of things. But there are applications that are risky, and we really want to do them, and we need AI to do them. But yeah, we need to take care of the risks, and there's a whole list of applications where this could be interesting. But yeah, this whole thing is still very much in discussion. I'll skip on that. Now, if we look at trustworthiness and how to achieve a trustworthiness, one aspect is what we call hybrid artificial intelligence, which has two main aspects. One is the human-centric AI approach. So how humans and machines, AI machines or agents can operate together. And the other one is the integration of different methods of AI, which is also known as neurosymbolic AI and different things, so data-driven and knowledge-driven together. And both, so the human-centric and the neurosymbolic approaches are both important. And if we make progress on both, then we can achieve much more trusted AI. So on the human-centric side, what we do want to achieve, according to, well, not everybody agrees on that, but I think there is a big community that supports this idea of human empowerment, in the sense that we want AI systems to support human activities and not to replace humans at all. So I would call this the symbiotic coexistence of biological and synthetic intelligence, and make use of the complementary capabilities, which requires that we also know about those. So mutual awareness of each other's strengths and weaknesses is crucial, which means that we need to be able to describe those. So both humans and agents have different types of knowledge and facilities, and resources, and we need to be able to make the expectations, the intentions, and the assumptions explicit in order to have a good collaboration. So that's again something to argue for a lot of transparency in designing the systems, but also in the interaction. Now, what is important also in this context is this theory of mind concept, which means that one actor in such a system is not only reflecting and reasoning about its own knowledge and goals, but also takes into account the mental states of other actors, both human and agents. So if we manage to describe the intentions of each of the parties and can reason with them in the social context, then we can make much more reliable and trustworthy systems. Then on the technical side, there is this notion of this third wave of AI, what I mentioned before, this combination of different paradigms of or approaches to AI. So it's also called neurosymbolic. We also nowadays call it neuro-explicit, because there are also things that approaches that are not not categorized as symbolic, but still explicit models like differential equations and that kind of things. And there is a huge understanding that there is this way forward of combining all these things, which is also reflected in psychology, like this thinking fast and slow. So there is a lot of evidence that the combination can bring us much further. Here is a comparison. I will skip this now because of time. But of course, all these approaches have pros and cons, and we want to make the best use of the combination of these approaches. So what we can do is to look at AI not as just a system of deep learning, but that is just one of the many aspects of a system. If we look at the whole context, we can say that what we can categorize as neuro-explicit AI is a combination of learning, using neural networks and deep learning and all these techniques, but also with reasoning, using knowledge representation, symbolic reasoning, but also acting in the context and understanding the context. So to have also this notion of agency and autonomy, where those agents can either communicate and learn from the context, but also can communicate amongst each other to form teams also with humans. Then if we look at the different ways in which you can combine all these different paradigms of AI approaches. A while ago, we had a publication to come up with a way to describe those combinations. So this is what's known as the boxology. So it was like starting from studying the literature and seeing all these different approaches and trying to systematically describe those approaches in terms of modular design patterns. It's based on 4 top-level concepts. So we have instances, models, processes, and actors with different graphical notations. And then we have we can create those patterns which relate those concepts to each other, and the whole taxonomy. So it's much more fine-grained than these 4 top-level concepts, but it helps to find a common language to describe those systems. So one of the examples is here that we have a simple pattern for training a model based on data. It's a typical machine learning system. Then we have the other part with the operational part, where we use the model with operational data and deduce symbolic output, so like a prediction or classification. And then we can put this together and have one composed pattern to describe this. So this is basically the standard machine learning approach. And then we can use it in different ways, like for example, here we have exactly the same pattern, as you can see, but then the input side is symbolic, so we can use it in ways like known in inductive logic programming, where the input, the data is are rules and statements of facts, and we can train a model with rules and can use that to use other symbolic output. Another example is this one, where we have we use a semantic model that describes parts of the known world, and we use this model as an input to training the data oriented model, which helps us to make distinctions and understand the context much better, because we know that certain things are look in a certain way, but maybe are not what it seems. And if we know that, for example, this chair, we have a certain rule here of that a chair is composed of different parts, and that this object in the middle is maybe not a real flower, but it is a cushion on the chair, because that's much more likely. So we can use this reasoning in order to improve the purely data-oriented machine learning system. And that is quite similar to also using a semantic loss function within the system. Another example is that we can we can train a model from data. So we use the input from an environment. We interpret that. We do a recognition of objects, etc., and then feed that forward to a second part of the system, which is symbolic, which does the reasoning and the decision making on the action that has to be performed within the environment again. So we have this feedback loop, and we use both sides, so the perception and the cognition in combination. And this is another example where we have also, in a similar way, we use perception, we use neural networks to detect handwritten digits, as well. A lot of people have been doing, but now if we want to do arithmetic on these digits, then it makes much more sense to do that in a symbolic way, because we don't want to do that on the basis of the bitmap. This is just another example that is also combining these two approaches in a very efficient way. And then there's, well, I'll skip this one. So now if we go and look at interaction in human agent teams, what we mentioned before already, so we do that based on the theory of mind, where we have explicit assumptions and mutual awareness of each other's strengths and weaknesses, that allows us to clearly define the roles and discuss about who can do what in a certain context. And we also tried to use our diagrams to represent this. So we have different types of interactions from agents and humans on the one side. So this is the internal part of the reasoning within the agent. And then we can also look at the team as a partner in the interaction. And in this case, we have a market mechanism where there's a market where, for example, an agent or a human can publish requirements for a task, which then can be picked up by members of a team, and they can make a bid, apply for performing this task, etc. So yeah, this allows us to both show the interaction between the different partners, but also the internal processes, which is a bit different from what has been done before, although the patterns themselves are, of course, not new. A similar one is here about the negotiation, where we have direct interaction between different parties. In the market, it's all it's more abstract, and so the market is in between the partners. but here we have direct communication. And then we also have a simpler form with the delegation, where we just one agent or human just specifies the tasks and asks for performing that one. And then we also have competition as another form. These are just examples of how you can model these interactions in human agent teams. And by being so clear and transparent and representing all the mutual expectations, we can generate trust within this interaction. And then, of course, I think I will skip this as well, because you probably will know about multi-agent learning and reasoning. So also this can be represented in these diagrams. There is, of course, this whole area of multi-agent reinforcement learning, where you have a set of states and actions, and then you have probabilities. And it's interesting to look at when the observations are not very certain. So you also have an uncertainty taken into account. But if you know about these guarantees that we can make by being explicit about the assumptions, and using also a point that I'm come back later if it's possible, about causality, then we can make the interaction, the negotiations, etc., are much more reliable and trustworthy in the end. So that brings me to the concept of if we really want to take all these parts that we've been discussing so far and create systems that are trustworthy by design, using this notion of epistemic orchestration, which means that we start from this boxology that I explained before, but we make it an instrument for design. So not just to visualize approaches that have been taken that we've found in the literature, but to really use it as a design methodology, and to be very clear about all the parts and the relationships between them. So we have to go a few steps further. So we need to have explicit representation of the mutual knowledge. So we use epistemic logic to do that, also to represent the intentions. And we model the causes and effects of certain actions within such a system. And that, of course, in this context of biological versus synthetical, or human versus artificial actors in an open world. And those representations that we exchanged and we communicate about, they can be, of course, predefined, but it can also be learned, as we've seen with the, for example, the multi-agent reinforcement learning. And then this is a further idea of like programming, not like we're used to doing procedural programming or declarative programming, but something I would call intentional programming. So we only want to specify what the intentions are of the different actors within the system, and they would organize themselves and figure out how to achieve the goals that we have defined, instead of saying exactly how to achieve those goals. So in this context of multi-party decision-making, what we need to define for such a system is the knowledge of each of the parties, so using epistemic logic, or the beliefs using the doxastic logic, a little bit different, but well, closely related. We need to define what each of them, of those actors, wants to achieve or wants to know. So that's their intentions as desired future states in the world. We need to define how they are related using causal relationships. So related in the sense of both the actors are related, but also how their intentions are related, how they can be achieved. And then we look at settings where the participants want to collaborate, but that's not necessarily the case. So they can also, we've seen further before, also in one of the patterns, there can also be competition. It does not always need to be collaboration in the sense that we have shared goals. But of course, that's one of the scenarios that we have shared knowledge and well, action and goals. You look at how we can form teams based on those and allocate tasks. We have to be transparent about all these aspects that I'm mentioning here. Yeah, one of the important things, again, is to be very explicit about the requirements, about things like the pre and post conditions of all of the parts within the components of the composed patterns. And this would allow us to do semi-automatic composition and generation of a system based on specifying those requirements. And finally, outlook to the future, of course, but it would allow us to verify that such systems are actually trustworthy in the sense that they comply with all the requirements that we have defined before. So if we look at how we can share knowledge, if we look at the representation of knowledge of each of those agents using epistemic logic, which is based on modal logic. So we can say that in this example here, you have the case that using this operator from epistemic logic, which is the K operator for knowledge. So agent A knows a fact phi 1, and agent B knows a fact phi 2, etc., etc. So each of them has individual knowledge. What we want to go towards now is to look at what's on the right-hand side here. So agent A knows that agent B knows that agent, etc., etc., knows a certain fact, which is exactly a representation of this idea of the theory of mind, where we take into account what other agents know, and we can make our decisions and our reasoning in the team based on this awareness of the knowledge and intentions of others. But of course, also this knowledge has to be updated. The world changes, etc. So there is this also known as dynamic epistemic logic, where we also introduce updates to facts, to parts that we know. And then another interesting aspect here is also the theory of mind aspect, is the distinction between group knowledge and common knowledge. So group knowledge means that in a system where you have a model and a certain state, satisfies an expression of conditions where the group knows that a certain fact is true, so that everybody knows that everybody else knows individually. So that is the group knowledge. So each individual within the group has knowledge about each other's knowledge, which is different from common knowledge, where we basically represent that certain facts are simply known. So we don't need to know explicitly who knows what, but we assume that, we are sure basically that that everybody knows certain facts within this certain group, which is of course if you have this, then it's easier to reason about. So you don't need to know all this individual knowledge. But of course, both are very important and have their applications. Now, if we look at how to model intentions, there are also ways. For example, with what is called the epistemic frames that can model the intentions as a set of strategic functions within the representation of a set of states that represent the world. And well, this is related to game theory, but can be used in other contexts as well. So this is an approach that we're using in order to have agents communicate about their intentions. So therefore, you're required to have them be represented in an explicit way. Yeah, and then you probably know about this, but I just want to make it clear as well. So this whole idea of correlation versus causation, there's a very nice example here, nice graphic as well, where here we see, for example, there is data about the number of sunburns and the number of ice cream sales in a given month of a year. So yeah, they seem to be highly, well, they are very highly correlated. So you could easily say, oh well, if I don't want to get a sunburn, then oh, I need to stop eating ice cream. But of course, there is no causal relationship between those two effects. Well, what is happening, obviously see, is that there is a third aspect, which is the number of sunny days in a given month that has that causes both those effects. So, well, correlation and causation are just very different. Another picture here to just show this. So the cause is the sun, and the two effects are correlated, but not causally related amongst each other. And having this kind of knowledge is very important to avoid making wrong conclusions on the one hand, but also to know if you want to achieve a certain effect and you know what the cause is of the effect, then you know how to what to do to achieve your goals. So this is a bit yeah, a bit more about this. So there's a whole language of causal diagrams and causal equations. So if we only look at statistical relations, we have just some correlation between a variable x and y. But with causal relations, we can say that x causes y, or the other way around, or there is actually a third variable that causes both x and y, which is here denoted as Z, which is known as a confounder in causal theory. And of course, you can make those diagrams, design them based on the knowledge that you have of a certain domain. But there is also work being done on causal discovery. So to find those relationships also within data, and you can do that with certain ways of doing experiments, randomized control trials, they're called sometimes, where you have a very controlled way of setting up the experiments so that you can guarantee that the causes, the causal relationships are different from the correlations. And of course, this is, well, there's not enough time to discuss this all in detail, but there is a whole theory of that from Julia Pearl, and this picture of his book here with different levels of understanding, where we have like association, basically the correlation level. And then if we try to find out how those variables are related through intervention, and if we even can think about what would have happened, then we are on the level of counterfactuals. Well, we can talk about this in more depth another time. Another thing, so what we want to develop here as well is to combine this approach to modeling intentions using epistemic logic and to apply it also to causal inferences, so to define an epistemic causal language, which would bring together those two worlds, and to include this part also in the team interaction to make it trustworthy and transparent. So this is another part of creating this goal of trust by design. And then, yeah, to finish, I would like to mention a use case where some of these ideas have been used. So this is called Talking Buildings. It's a project where in an urban context where houses and apartments and inhabitants of those apartments are all modeled as agents with mutual awareness of their preferences, their intentions, their preferences about energy consumption, about the temperature they want to have, the light, their habits, behavior, when they are at home, when they're not at home, etc. And in this interaction within those teams, create a trustworthy environment to optimize energy consumption in the end. So it's yeah, it helps to make the context much more sustainable. Yeah, so what is being done there is that intentions are shared, also called policies in that context. So to optimize energy consumption, well, optimize in the sense of reduce, of course, to have efficient interactions with the power grid and the usage of the buildings, and also to optimize the logistics, but also the safety around the buildings. So this is a good example that shows how all of these ideas can be used in a concrete application. And well, in the context of hybrid teams, where we can also, by making all these things that we mentioned before explicit, we can also explain exactly why certain actions are taken. And that helps to create trust. I mentioned in a recent newsletter of DFKI, there's an article that we wrote with some ideas, so you can look that up if you want. It's a link here. It's on the main website, you can find that. Also the contact details. We're also very much busy driving these ideas forward in the European Network of Excellence called TAILOR, which is exactly about creating trustworthy AI. So you can also find us there. And then, yeah, finish off with some greetings from around here. The weather is not so nice today, but that's where we are at the moment. And so I would conclude with that and ask, open for questions and discussions.
Yeah, thank you very much.
We still have some time for that.
Yeah, thank you very much, André, for your very interesting talk. So now we stop the recording and take Q&A